Today, we're diving into a critical piece of research from James Hansen, Pushkar Qureshi, Dylan Morgan, and Jason Vest, titled Super El Nino. Super warming is the main issue, published on March 20th, 2026. This paper suggests that while the discussions around a super El Nino are getting a lot of attention, they might be distracting us from an even more profound and urgent concern: the extraordinary acceleration of ocean surface warming.
That's exactly right, Chloe. The paper starts by acknowledging that models predict an El Nino beginning this year and peaking in early 2027. Some reports are indeed hyping a super El Nino, and understanding its strength and frequency is important because El Ninos significantly impact global weather patterns.
So before we get to the main issue, can you quickly clarify how El Ninos actually work? Many people hear the term but might not fully grasp the mechanics.
Certainly. The more common state in the tropical Pacific is La Niña, which is essentially the ocean's response to the prevailing easterly trade winds. These winds push warm surface water towards the west, causing cold, nutrient-rich deep water to upwell along the coast of South America. This supports rich marine ecosystems. An El Niño event, however, is triggered by tropical wind bursts from the west that weaken or even reverse these trade winds.
And when that happens, the warm water shifts.
Precisely. The warm surface water, which normally piles up in the west, with sea levels up to half a meter higher near Indonesia than South America, then sloshes back towards South America. This warming of the surface water there prevents the cold, dense, deep water from upwelling, leading to a decline in coastal biological productivity.
And the paper mentions Kelvin waves as a key component of this heat transfer. How do those contribute?
Kelvin waves are essentially large thermal waves in the upper few hundred meters of the ocean. They act as a conveyor, transporting heat from the western Pacific eastward. When these waves surface, they warm the ocean surface in the eastern tropical Pacific, transferring heat to the atmosphere through increased evaporation, which enhances global warming.
Given that understanding, the paper seems to suggest that predicting a super El Nino so soon after the 2023-24 event is a bit surprising unless human-made warming is playing a role. What's the latest on whether we're heading for a super El Nino or not?
The paper notes that the Nino 3.4 sea surface temperature anomaly is still in negative La Niña territory. However, the 300-meter heat anomaly, which is a better predictor of El Nino's strength and offers a longer lead time, implies a change is coming. The current heat content started early and is rising rapidly, similar to past super El Nino. Whether it becomes a super El Nino depends on the strength of future Kelvin waves, which are influenced by equatorial winds.
So, while El Nino is significant, the authors argue that something else is far more critical. They highlight an extraordinary acceleration of ocean surface warming. What makes this the more important concern?
The authors contend that El Nino discussions, while relevant, distract from the fundamental advance in climate understanding over the past 5 years, the realization that equilibrium climate sensitivity is substantially larger than the long-standing best estimate. This accelerated ocean warming has impacts like a factor of 2 greater warming over land, increased extreme precipitation, and a poleward movement of subtropical conditions. These are direct, ongoing consequences of a deeper problem.
You mentioned equilibrium climate sensitivity. For our listeners, what exactly does that mean? And why is this substantially larger estimate such a big deal?
Equilibrium climate sensitivity, or ECS, refers to how much the Earth's global average surface temperature will eventually rise if the concentration of carbon dioxide in the atmosphere doubles and then stabilizes. The long-standing estimate for doubled CO2 was about 3 degrees Celsius. The new understanding, backed by multiple data sources, indicates it's actually closer to 4 to 5 degrees Celsius. This higher sensitivity means that, for the same amount of greenhouse gases, the planet will ultimately warm much more than previously thought.
Why was there such an underestimate for so long? What changed in our understanding?
The underestimate stemmed from 2 main issues. First, there was an implicit assumption that aerosol climate forcing, the cooling effect of pollutants in the atmosphere, changed negligibly during the period of rapid linear warming that began around 1970. Second, climate sensitivity assessments relied heavily on observed warming over the past century. Aerosol cloud modeling now reveals that aerosol cooling actually increased during the 1970 to 2005 period due to the increased global spread of aerosol sources. This means that to account for the observed temperature rise, the underlying climate sensitivity must be larger than 3 degrees C.
So essentially, aerosols were masking some of the warming, and now that we're reducing those aerosols, particularly from East Asia and shipping, we're seeing the true, more rapid warming, combined with this higher climate sensitivity.
Exactly. High climate sensitivity, combined with the reduction of aerosol sources in the past 10 to 15 years, is what drives the accelerated sea surface temperature warming we're observing.
The paper presents 4 independent assessments for this higher climate sensitivity. Could you walk us through the most compelling ones?
The first and arguably the best measure comes from comparing the last major ice age, 20,000 years ago, with the present interglacial period. Researchers like Jessica Tierney, Matt Osman, and Alan Seltzer have shown the ice age was about 6 to 7 degrees C colder, not the 4 degrees C previously assumed. After accounting for differences between land and ocean warming and the effect of large ice sheets, this comparison of 2 stable climate states provides a strong measure of climate sensitivity, 4 to 5 degrees C for doubled CO2.
That's a significant revision. What's another key piece of evidence?
The second source is the large reduction of Earth's albedo, or reflectivity, observed since the year 2000 through precise satellite data. Most of this reduction is attributed to fewer clouds reflecting sunlight. This implies that clouds are a strong amplifying climate feedback. If clouds were neutral, climate sensitivity would be much lower, around 2.4 degrees C. The observed large cloud feedback suggests a climate sensitivity of at least 4 degrees C.
And the third piece of evidence mentioned is quite intriguing, the last snowball Earth event.
It is. About 600 million years ago, Earth was a snowball with ice reaching the equator. The sun has slowly brightened by about 6% since then. A 2% change in solar irradiance is equivalent to the climate forcing of doubled carbon dioxide. So that 6% change is like 3 doublings of CO2. The fact that such a modest solar change caused a snowball Earth implies a high climate sensitivity, again around 4 to 5 degrees C for doubled CO2, and even higher if you include ice sheet changes.
The fourth source of information, the paper states, is the least accurate. Observed global warming over the past 1 to 2 centuries, which is often the focus of IPCC reports.
That's correct. This method is less accurate because it requires precise knowledge of the net climate forcing that drove the warming. While greenhouse gas forcing is well understood, aerosol forcing was not directly measured. The IPCC's previous best estimate assumed aerosol forcing was essentially unchanging during the 1970-2005 period of rapid warming, which led to a climate sensitivity estimate near 3 degrees Celsius. However, new modeling shows aerosol cooling actually increased during that period due to the global spread of sulfur dioxide emissions, even if overall emissions didn't change much. This means aerosols offset about a third of the greenhouse gas forcing.
So, if aerosols provided more cooling than previously thought, then to achieve the observed warming, the climate system itself must be inherently more sensitive to greenhouse gases. This pushes the ECS up to around 4.5 degrees Celsius.
Exactly. The paper makes a strong case that a climate sensitivity as low as 3 degrees is now ruled out with over 99% confidence. This reevaluation, coupled with the understanding that aerosol cooling was underestimated, means there's additional warming in the pipeline as we continue to clean up our air. These are 2 independent factors, but together they fundamentally change the climate story.
This seems like a massive paradigm shift. Why isn't this widely accepted or incorporated into all climate models yet? The paper hints at some resistance within the scientific community and media.
The authors suggest that climate models, which have been developed over decades, had their sensitivity parameters set based on the assumption of negligible aerosol change between 1970 and 2005. If a model was developed under that assumption, it would need a sensitivity near 3 degrees Celsius to match observed warming. Changing these fundamental parameters isn't easy. The authors feel there's a reluctance to revisit these foundational choices, preferring to stay within the model fog rather than acknowledge new evidence that challenges these long-held assumptions. They highlight how some experts in the media might shut down discussion of new findings with ad hominem criticisms rather than engaging with the physics.
It sounds like the core message here is that the Earth is significantly more sensitive to greenhouse gases than we previously understood, and that the reduction of aerosols is now revealing this underlying, faster warming. This isn't just about El Nino, it's about a fundamental reevaluation of our climate future.
That's the takeaway. The switch from a net forcing of about 0.3 to 0.6 watts per square meter per decade is why Earth's energy imbalance has doubled and global sea surface temperatures are accelerating. The authors emphasize that accurately informing young people about this situation is crucial for helping them deal with what they're inheriting.
This has been a truly illuminating discussion, Alex. The findings from James Hansen and his co-authors certainly give us a lot to consider regarding the true pace and scale of global warming. To our listeners, if you found this conversation insightful, Please share this episode with someone who might also benefit from understanding these critical climate insights.